With the t-shirt order forms, if you know some of your colleagues, like the school that might want one, I mean, I'm just not limiting it to only my students, I'd really like to, but, because of this, anyway. So if you have other people that, if you want to, I can print out the form if you want to see like more forms, or if I can print out like a sheet that has it, if they want to see what it's like. So if you have other peeps that might want one, let me know. Okay, so let's start this up.
Action.
Action, we're rolling. Okay. So we're recording this lecture because a bunch of people are gone. For whatever reason, this video is not out on YouTube. Just act yourselves, because we're going to be okay. Right? Just normal participation from the studio audience. So, here's what we're going to do. And today's lecture is going to be brought to you by the word syringe, okay? Which is kind of weird that a physics lecture is going to be based upon a simple syringe, but here's what's going to happen. So, here's what we've got to work through. On the lecture notes that I gave you all yesterday, okay, the thermodynamic lecture notes, the whole heart and soul of what we're going to talk about today is going to be what's going to happen back here with three different processes: isothermal, isobaric, isovolumetric. So the first thing, and a lot of this stuff that's on the lecture notes is stuff that we've already talked about. But so here's what we've got to get through. So today we're going to get through the last of the thermodynamic stuff, these processes. Then we got an assignment tonight. Then on Monday we're going to get through buoyancy and the Archimedes principle. Got an assignment then. Then we'll review on Tuesday, test on Wednesday. So today you will get your second to the last physics assignment. And then on Monday you will get your... The correct response is...
Oh, dang it.
Okay, not your
I'm
recital.
crying inside.
Whatever.
Hate me.
Stan and I have no doubt that you're crying inside. Okay, I can tell because that little bob on top of your hat kind of, does this when you cry inside. Okay, it kind of does this. Okay, anyway, so as we go through this, it's going to seem very complicated at the beginning, and you're going to think, my God, there is no way that I'm going to understand this. It's just horrible, okay? And at the beginning, it is going to seem very daunting. But if you keep in mind the terminology and what's happening, trust me on this one, you're going to get through it. And at the end, you're going to go, oh, okay, that makes pretty good sense, okay? So the whole basis of this is what's called a pressure volume graph. So you're going to have pressure here. And then you can have volume. Hold on, I can change this so the studio audience can see it. Volume.
Oh, we're back to the big one.
We're back to the big one. Okay? And then you got cubic meters. Okay? Now, what's pressure going to be measured in? It could be in torrs, it could be in inches of mercury, it could be millimeters of mercury, atmospheres. What do you think this is going to be in? Well, pascals, which is the same thing as
Newtons per meter squared.
Newtons per square meter. Okay? So, now, let's just say that we're going to draw a horizontal line across here, right? So, if I draw a horizontal line across here, what do you think is the pressure changing, or is the pressure staying the same? Same. Okay? So let's say that this is just to make up a number. Let's just say this is 1,000. Okay? I'm going to change the scale in just a second. This is just to give us an idea. So this is 1,000, right? And let's say this volume is 5 cubic meters. So if I take 1,000 newtons per square meter times 5 cubic meters, what do I get? Well, I get 5,000, right? Let's start with the basics. But then I've got newtons per meter squared, right? Multiplied by cubic meters. True? Okay? So, if I do this, what units do I get?
Newton meters or joules.
Oh, Newton meters or joules. Wow. Okay? So, here's the first thing. Is that the area underneath a pressure volume graph is measured in joules. And this is going to be important. this is going to represent work that was done either on or by the gas. So what you'll see is that to understand this process, this is all about prepositions, okay? In the sense that is work being done by the gas or is work being done on the gas? Is energy flowing into the system? Is energy flowing out of the system? Okay? So this is going to boil down to those four prepositions. By the gas, on the gas. Into the system, out of the system. Okay? So those are going to be the two biggest things that you have to keep track of. So if ever you're going to reach a point where you're going to memorize stuff, you've got to memorize and understand those four bits. So what I'm going to do is I'm going to work through one big complex process. We're going to start simple, and then once you figure out one of these processes, then everything else begins to stay the same. Okay? Because literally it just becomes variations on the theme. So with that said, that's not what I want. Where's the sheet that I want? Where's the sheet that I want? There it is. Nope, that's not it. There it is. Okay. So we're clear the board, and here's what we've got. So this is okay. All right. So here's what we're going to do. On the back side of these notes, there's three different processes we're going to look at. Isothermal, isobaric, and isovolumetric. So if you remember back into the days of your misguided youth as freshmen, okay, you took the freshman geoscience class. And I guarantee you, one of the things that you did is that you had a map of the United States and you drew lines of equal pressure or lines of equal temperature. Does anybody remember what lines of equal pressure are called? Trent?
Is it isometric?
Close.
Isomers?
Isomers, right? They're technically isobars,
I
okay?
remember that.
Right?
Freshman
I
year.
don't think I did.
And then lines of equal temperature are called isotherms, okay?
We did not want
It was.
I promise you,
Who
you
did you
did.
have, Caitlin?
You all slept since then, but I promise you, you did. Okay. You don't even remember the name of the teacher?
I had Syl and
I had
Same.
Syl as well. Were we in the same class?
Yes.
Oh, yeah, that had to be trouble. You two as freshmen? Whoa, step back. Okay, so ISO just means the same, okay? ISO just means the same. So if you're talking about an isothermal line, guess what? You're talking about always the same temperature. If you're talking about isobaric, you're talking about constant pressure. If you're talking about isovolumetric, you're talking about constant volume. So those are the three that we're going to deal with, and they're on the back of the lecture note. So what we're going to do is we're going to work through all three situations. So what we're going to do is we're going to start up here with a gas that's under this much pressure, 2.44 times 10 to the third newtons per square meter. Now to give you some perspective, right? So this is 2440, okay? 2,440 newtons per square meter. That's the pressure of the gas. Now to give you some comparisons, right now you all are under 1 atmosphere of pressure. So your pressure right now is 101,300, okay? So you're under a lot more pressure than what is happening inside this system, okay? This seems like a lot, wow, 240,000, right? Well, not really, because you all are under a much exponentially higher amount of pressure right now. So I'm just going to have this as a number. So here's what's going to be important. Is that on the pressure volume graph, here's what you can also figure out like a third set of data. So when you look at this and you got 2.44 times 10 to the third newtons per square meter. and you have a pressure. So this is like an X and Y coordinate system that says, okay, here's my X component, 0.1 cubic meters. My Y component is the pressure, okay? Now, here's the other thing. You also have to remember, and this is going to be the key to this, that PV equals nRT. So what you want to look at, I got to remember what the volume is, 0.1 moles. Okay, so when you look at this, in all of these processes, we're going to keep the same number of moles, which for this example, we're going to have 0.01 moles. So throughout this, we're not going to change the number of moles of gas. We have the ideal gas law constant. That's not going to change, 8.314. So at this point, I know a pressure, and I know a volume. I know my N is 0.1, and I've got a value of R, known value. So what else can I find at any point? If I know a pressure and a volume at any point on this graph, what else can I find? Find the temperature. So in a sense, it's like a three-dimensional graph, in the sense that in 2 dimensions, you have pressure and volume. But a third dimension will always be the capacity to find a temperature. As long as you know what N is and you know what R is, you can always find a third point. So that's gonna writ large in this whole theme. You have 2 points, but at any point you can always easily find a third value. Okay? So we're going to start here. I got this pressure, and I've got this volume. So can I find the temperature of the gas? Yes. It's just weird with you with that cop hat on. I look up and it's like,
No, leave it on.
yeah, you can leave it on, but it's just kind of flipping me out. That's all. It takes me back to being arrested in Africa. Okay. I'm just kidding. I was never actually
So
arrested.
not kidding.
Okay. So, if I know this pressure, and I know this volume, and I know that I've got 0.1 moles, can I find the temperature? Emma, what am I going to do to find the temperature knowing pressure, volume, N, and R?
Take the pressure times the volume and then divide it by N.
Beautiful. So, I'm going to get temperature by itself. So, I'm going to figure out the unique temperature that's going to make this happen. So, I'm going to take the pressure, volume, divide it by NR, and that's going to get me T, right?
Yes.
So, somebody take 2.44 times 10 to the third newtons per square meter times a volume of 0.1 cubic meters. So that's 2.4 times 10 to the third for those of you in the studio audience. Okay, that's this number. And then we're going to divide by N, which is going to be 0.1 moles, so we don't have a lot of gas in there. And then I've got an R of 8.314 joules per mole Kelvin. So at this point, the moles are going to cancel out. This up here gets me newtons per meter squared times cubic meters. That gets me joules on top. So that cancels out all of that. I've got Kelvin left down below. There we go. We're in the wheelhouse. So what temperature is going to correspond with this? So basically, that's going to cancel out. So it's 2440 divided by 8.314.
293 Kelvin.
293 Kelvin. Oh, okay. Now, how can I figure out what temperature that is in Celsius?
Subtract 270.
Subtract 273, and I'm going to get 20 degrees Celsius, which is about where we're at right now. So this gas is at about room temperature. Okay? We're not like at the surface of the sun. We're not boiling water. We're not, stuck in deep freeze. This is about room temperature gas. Okay? All right. So the first thing that we're going to go through, and it's going to be the most complicated one. So I'm going to go through the most complicated one first, and then the other ones will become more simple. So we're going to start with the most complicated one, and then if you can understand that, everything else is gravy. All right? So let me kind of get rid of all of this. So the first thing we're going to deal with is an isothermal system. So in an isothermal system, what's going to stay constant?
Temperature.
temperature is, right? Isothermal, constant temperature. So what we're going to do is we're going to take this graph and we're going to go from 0.1, okay, with this, and we're going to expand this gas to 0.5. So you have to visualize what's happening. So this is why I have to have this syringe. So here I am, let's just say this is 0.1, okay? So I'm at 0.1 cubic meters. I want to make this volume go to 0.5. So am I going to push the syringe down or am I going to pull the syringe up? I'm going to pull the syringe up. Now, here's what's important. This is going to be a sealed system. So I've got to hold my thumb over the end of it. Because why can't I just pull this up and then make it go that way? Because if I don't put my finger over the end, what's going to happen? Well, what am I going to allow in? I'm going to allow in more moles of gas. Okay? So I've got to have this as a sealed system. So here I am at some point, we're going to call 0.1. I'm going to put my finger over the end of it. And then I'm going to pull back on that. So I'm going to make my volume get bigger. So I'm going to go from this point to this point. I'm going to change up the colors because I can. So, woo! So I'm going to come down here like this. Okay? Now, here's the deal. This all boils down to understanding the ideal gas law equation. That PV equals nRT. So what did we say our temperature was?
20.
No, I mean Kelvin.
Oh, 293.
293. So here's the most important part of this. This is 0.1 moles. That's how many moles I have in the system. Okay? 0.1 moles. I have an R, which is 8.314. And then I've got a temperature, which is, we said 293 Kelvin. So somebody take 0.1 times 8.314 times 293.
244.
244. Now, what units do I have over here? This is joules per mole Kelvin, or joules, right? So the right side of this equation is 244 joules. So here's what's most important. When I go from here to here, what am I doing to the volume? I'm increasing it, right? But this side is staying the same. This side always has to equal, in this situation, 244. So when I multiply this pressure and volume together, I always have to get 244 joules because it's an isothermal situation, right? So if I go from here to here, I always have to get 244. So as my volume is going to get bigger, what has to happen to my pressure?
Decrease.
It has to decrease. So this is why this line is an inverse relationship graph. Because the two numbers multiplied together, in this situation, always have to equal a constant of 244. So I'm here, I'm coming down like this. This is an inverse graph, which you all have seen before, right? Cool with this. So, when I get to this point, okay, now I know my volume is increased to 0.5. So can I find the new pressure that goes with that? Yeah, because what do I know my pressure and volume have to multiply together to equal? 244. So if I want to find this pressure over here, which we said has to be less, which it's going to be, I can take my volume, which is 0.5 cubic meters, and that's going to equal 244 joules. So my pressure times my volume has to equal 244. So somebody figure out that pressure. So should be 488, okay? 488 newtons per square meter. So look at this. Initially I had a pressure of 2,440 newtons per square meter. Now I've dropped that down to 488. So now let's look at this. What's happening on an atomic level? Here's the other thing that you have to visualize in terms of what's happening on an atomic level. So we're going to talk extensively with Timmy and his second grade class. Okay? So here's Timmy's second grade class. Okay? And here's Timmy's, and we got a certain number of Timmy's running around, okay? So here's the deal. We're going to change something within the room, okay? So on an isothermal, remember, what does temperature indicate? When you're measuring temperature, fundamentally, what are you talking about?
Kinetic energy.
The amount of kinetic energy of each Timmy, okay? So we're going to keep the kinetic energy of Timmy's the same. No Skittles are allowed in, no nap time, nothing. The Timmys are going to maintain a constant kinetic energy because we're not changing the temperature, okay? We're not changing the temperature. Now, we have pressure sensors around the room. And the pressure sensors are activated every time Timmy runs into them, okay? So the Timmys are going to be hitting the pressure sensors with the same amount of force because the kinetic energy is staying the same. So Timmy's still going to be hitting the wall with the same amount of energy. We're not going to slow Timmy down. We're not going to speed Timmy up. Timmy's going to hit the wall with the same amount of force every time. But look what we've done. What have we done to the size of the room? We went from 0.1 to what? 0.5. So instead of having this size of room, now we're going to have a much bigger room because now we've increased the size of the room because we've made the volume bigger. But we're going to have the same number of Timmys running around inside the room. We're going to have the same number of Timmys, and we're going to have the same amount of kinetic energy. So what do you think is going to happen to the number of collisions with the pressure sensors? It's going to decrease, okay? Because it isn't because we have fewer Timmys, and it isn't because of the fact that the Timmys have less kinetic energy. We're going to see a decrease in pressure simply because there's more room for the Timmys to exist. Okay? Does that make sense? So there's two. If you see a drop in pressure, something had to change. So if you see a drop in pressure, one of two things has happened. Either the Timmys aren't moving as quickly when they run into you, or there's just not as many Timmys hitting the pressure sensors. Okay? And that's what's happening here. We've made the room bigger by quite a bit. We have the same number of Timmys, they have the same amount of kinetic energy, but there's just not going to be hitting as many. Does that make sense? Okay. Now, so we've got this line, right? Now, the area underneath this line is going to represent the work. Okay? Now here's the kicker. This is a curved line. It's not a linear line. This is a curved line. So to try and find the area underneath this graph, we cannot treat it like a triangle because we've got to do some calculus. Now, don't flip out and go, oh my God, we're going to do calculus. No, I haven't done this. Okay, it's okay. It's all cool. So, if you'll notice on this handy-dandy equation sheet, on an isothermal, I've got work equals, and if you ever need to have this equation, I will give it to you. Work is going to equal nRT, natural log VI over VF. So let's talk about this equation. And we're going to do the math on this because we're going to find this area. So what we've got is that work is going to equal nRT, natural log of VI over VF. Okay? So my N is 0.1 moles. All right, that's cool. I've got my R, which is 8.314 joules per mole Kelvin. Our temperature was 293?
Yeah.
293 Kelvin. So at this point, what units do I have?
Joules.
Joules, because the moles cancel out, the kelvins cancel out, so everything here is going to be joules. So somebody take 0.1 times 8.314 times 293.
244.
244. Okay. 244 joules. Now, let's talk natural logs. I'm guessing at some point you all have been exposed to natural logs? Okay, a vague idea. Here's the main point. What we need for today's lesson is that you can punch a number into a calculator. That's the main thing I need out of you. It is theoretically a whole another mathematical description where you talk about e to the negative natural log, you do all this good stuff. Today, you just need to be able to hit a number on a calculator. That's all I need you to do. But you have to understand the ramifications of this. Now, notice this is volume addition over volume final. What was my initial volume?
0.1.
0.1 cubic meters, right? My final volume is 0.5 cubic meters. Now here's what's important. This is absolutely vital that you understand this in terms of sign, okay? This is so important, and I cannot emphasize this enough, the importance of signs when it comes to thermodynamic calculations. Okay, if you thought I was nuts about signs doing like velocity and frame of reference, you haven't seen anything until you get to this. Okay? So here's the deal. I got 244. When I take, and all I want is just a broad idea. If I take 0.1 and divide it by 5, do I get a number bigger or smaller than 1 that I'm going to take the natural log of?
Oh, bigger than 0.1, sorry, it's smaller than 1.
But yet, it's like 1 divided by 5 is 0.2. So I'm going to be taking the natural log of a number less than 1. So whenever you take the natural log of a number less than 1, is that a positive or negative value?
Negative.
Negative. This is going to play out huge, okay? Huge. So when you take the natural log of any number less than 1, it's a negative number, okay? It's a negative number. So out of all of this, this is the only thing that can generate a negative value for me. So somebody take 244 times the natural log of 0.1 divided by 0.5.
Negative 392.
93.
Oh,
Negative what?
393.
Negative 393
No,
joules.
you're rounding. You're rounding too much. Negative 392.
Ruh-roh.
Fight. It's negative 392. You gotta take the whole answer.
This is dumb.
This, it's close enough. We'll go with 390. Okay. Now, here's the significance of this negative sign. This is a negative value. Okay? Listen to me. This is a negative value. Now, did the volume get bigger? Yes, the volume got bigger. When the volume gets bigger, work is going to be a negative value. Okay? Now, here's the reason why this is a negative value. So, what had to happen? And this is where you have to understand this on a microscopic and macroscopic level at the same time. And like I said, this is going to seem weird and say, oh my God, there's so much to think about. It's all going to be good. Okay? So, what physically had to happen is that something had to push or cause this plunger to go back. It had to go from 0.1 to 0.5. Something had to move this plunger because it's not going to move on its own. Okay? Just like all objects at rest remain at rest, something had to make this plunger move. Now, if you remember from yesterday, actually let me go get that. Stop that for a second.